Hi everyone, my name is Tho Nguyen. I'm a PhD candidate at Nanyang Technological University in Singapore. My supervisor is Professor Tho Nguyen from Nanyang Technological University, Singapore. My co-supervisor is Professor Douglas L. Jones from University of Illinois at Urbana-Champaign, USA. My research interests are deep learning, audio signal processing, microphone array, and real-time signal processing. Today, I'm going to present our paper, a sequence matching network for polyphonic sound event localization and detection. We humans can effortlessly localize and recognize multiple sound sources at the same time, and these tasks are exactly what a sound event localization and detection system aims to do. Sound event localization and detection, short form SELD, that uses small arrays consists of two subtasks, which are sound event detection SED and direction of arrival estimation or DOA estimation. These two subtasks are mutual resource topics. However, joining these two subtasks are not trivial. SED and DOA estimation require different information from the audio input signals. SED mainly relies on time frequency patterns, while DOA estimation mainly relies on phase or magnitude differences between microphones. However, SED can potentially improve the performance of DOA estimation by providing accurate acoustic signal detection. Likewise, DOA estimation can potentially improve the performance of SED by spatial filtering to reduce the interferences in multiple source conditions. To solve sound event localization and detection problem, Adavan et al. Proposed a single input, multiple output convolutional recurrent neural network (CRNN) called SELDNet that jointly optimize SED and DOA estimation. However, the joint optimization reduced the performance of each task. To mitigate this problem, Tho et al. Proposed a two-stage strategy to train two almost identical CRNN models for two tasks separately. First, a CRNN model is trained for SED. After that, the CNN weights of the SED model are used to initialize the CNN layers of the DOA model. The SED outputs are used as masks to select the corresponding DOA outputs. These two-stage strategies significantly improve the SELD performance. However, the errors made by SED model will propagate to the DOA model, and the DOA model tends to learn unwanted association between the sound classes and the sound directions. We propose a different method to combine SED and DOA estimation. We observe that each sound event has three attributes of interest. First is timestamp, onset, offset. Second is sound class, and third is DOA. A sound event detector outputs the timestamp and the sound classes, while a DOA estimator outputs the timestamp and the directions. Since the overlapping sound events often have different onset and offset, we can match the active segments in the output sequences of a sound event detector and a DOA estimator to associate the sound classes with the corresponding directions. The figure on the right shows the ground truth and the predicted sequences of a sound event detector and a DOA estimator. Based on the onset, offset, and the durations of the events, we can visually associate the sound classes and DOAs of the same sound events. Errors made by each individual components can be potentially corrected during this late fusion process, such as false positive in the SED output sequences or missing segment due to weak signal in the DOA output sequences. To match the output sequences of sound event detector and a DOA estimator for sound event localization and detection, we propose a sequence matching network as shown on the screen. The sequence matching network takes the SED output sequences and the DOA output sequences as input features. The main component of the sequence matching network is a bidirectional gated recurrent unit GRU that combines these two input sequences together and take into account their temporal information. Because the number of DOAs is much larger than the number of cell sources, the cell classes, a convolutional neural network CNNs is used to reduce the directional dimension of the DOA output sequences. This modular and hierarchical approach increases the flexibility in designing and optimizing models for both SED and DOA estimation. The sequence matching network not only acts as a late fusion model to improve the onset of set predictions for the cell event, but also match the cell classes and the corresponding DOAs. For each time frame, the sequence matching network outputs the number of events, the cell classes, the azimuth, and the corresponding elevation. Next, we will discuss the detail of the SED network and the DOA estimation module. The SED network is borrowed from the SED network of the two-stage paper by Cao et al. Input features to the network are log-mel and GCC fat. The network consists of 4 CNN layers, followed by a bidirectional GRU and a fully connected layer. The SED outputs for each frame are the posterior probabilities for all the cell classes. We use random cutout for data augmentation to improve the SED performance. This data augmentation was not used in the original paper. For DOA estimation, we use a single source histogram analysis method to estimate the directions of arrival of multiple cell sources. The input features to the DOA estimation algorithm are the multi-channel complex spectrograms. The algorithm selects time frequency bins that are above a noise floor and contain energy mostly from one source to mitigate the problem of noise, reverberation, and multi-source. For each selected time frequency bin, a DOA is estimated and populated into a 2D histogram for each time frame. This histogram is then vectorized to form the DOA output sequence. The conventional output format for SELD problem could not handle the case where two overlapping cell events had the same cell class but different directions. We propose a new output format that can handle this problem. The new output format predicts the number of active events, cell class, DOA for each event up to a predefined number of maximum events. This new output format do classification instead of regression for DOA estimation. Therefore, it is potentially easier to optimize the cost function. We use the spatial cell events dataset with ambisonic format to evaluate our proposed approach. This public dataset was also used for the decay cell event localization and detection challenge last year. The dataset consists of 401-minute recordings for development and 101-minute recordings for evaluation. The data are synthesized using recorded room impulse responses and clean signals. There is a maximum of 2 overlapping cells in each frame. The dataset consists of 11 indoor cell classes and 324 directions of arrival in 3 dimensions. We use the SELD evaluation metrics that were proposed for the DCASE SELD challenge last year. The SELD task is evaluated for SED and DOA estimation individually. The metrics for SED are segment-based error rate and F1 score. The metrics for DOA estimation are frame-based DOA error and frame recall. Since the conventional SELD evaluation metrics decouple the two tasks, we introduced 2 new metrics that account for the correct association between the predicted cell classes and the estimated DOAs. The first metric is the frame-based matching F1 score. This is the F1 score that takes into account only the frames with both correct cell class prediction and correct DOA estimation. The second metric is the frame-based same class matching accuracy. This metric looks at all the frames that have 2 overlapping events with the same cell class but different DOAs and compute the portion of the events that have the correct predictions. We compare our approach with several state-of-the-art SELD algorithms. The baseline are the SELD net and the two-step method. The two-step augmentation is the two-step method with additional random cutout for data augmentation. The SED net is the SED network of the two-step method with augmentation. The DOA-HIST is the histogram algorithm for DOA estimation. Both the SED net and the DOA-HIST produce the input sequences to our proposed sequence matching networks. We denote the proposed sequence matching network with the conventional output format as SMN and the sequence matching network with the new proposed output format as SMN event. We also list the results from the top two teams in the decades challenge last year. These two solutions are based on ensemble approaches. The SELD evaluation results are now shown on the screen. The up arrow for a metric indicates the higher the better. The down arrow indicates the lower the better. We can see that the two-step method outperforms the SELD net. The two-step augmentation is better than the original two-step, especially with the SED error rate and F1 score. The SED net is the SED network of the two-step method with data augmentation. Therefore, the SED score are the same. The DOA-HIST have the lowest DOA error among all the baselines. The SMN significantly improved the evaluation metrics for both SED and DOA estimation. The error rate of the SMN is 0.079 compared to 0.108 of SED net. The F1 score of SMN is 0.958 compared to 0.944 of the SED net. The DOA errors of the SMNs are slightly higher than the DOA error of the DOA-HIST, but still significantly lower than the DOA errors of the baselines. The DOA frame rate of the SMNs are also significantly higher than the DOA frame rates of all the baselines. Our SMN results are also comparable with the top two teams in the decades SELD challenge. The Kapka ensemble heavily used heuristic rules to determine the single source and the two source segments of the signal to infer the subclasses and the DOAs. As the result, their DOA errors is low and the DOA frame rate is high. However, the heuristic rules only applicable for two static source scenario. The two-step ensemble use both ambisonic and microfold array format and combines many different models for the ensembles. Compared to these two ensembles, our SMNs are more lightweight, and the SED score of our SMN are slightly better, while the DOA scores are lower. When evaluating using the two new metrics, the SMN significantly improved the matching F1 score and the same class matching accuracy. This shows that our approach is better at matching the subclasses and the DOAs compared to the baselines. Furthermore, the SMN event is the only network with the new proposed output format. It doubled the same class matching accuracy compared to the SMN with the conventional output format. This shows that the new output format is very promising for the SELD problem. So in conclusion, our proposed sequence matching network outperformed the state-of-the-art SELD net and the two-step method for sub-event localization and detection. The sequence matching network is modular and hierarchical. Therefore, it can improve the performance while increase the flexibility in designing and optimizing its components. The sequence matching networks increase the correct association between the subclasses and the corresponding DOAs in multiple source cases. The new output format can also handle the cases where multiple sub-events of the same class have different DOAs. And finally, the new evaluation metrics address the problem of matching subclasses and the DOAs, which were not achievable using the conventional SELD evaluation metric. Thank you very much for listening. Next is Q&A.